Hello and welcome to Lecture 2 of the Oscillations unit of Phys 1201, and this lecture is going to be all about simple harmonic oscillations. And there's a lot to know about simple harmonic oscillations, so we will not be done at the end of this lecture. But the main point of this lecture is that we're going to see the two quite different defining features of simple harmonic oscillations. Let's talk about the simplest case of a simple harmonic oscillator. If it's a vertical oscillator, then we have to worry about a spring force and a weight. Now that actually doesn't make things any more complicated, but it takes a little bit of effort to show that it doesn't make things any more complicated. So let's start out with this horizontal case. So we have a mass, it's on a frictionless surface, so maybe it's an air puck or a glider on an air track or something like that, and it's attached to a spring. And it's sitting here at the equilibrium length of the spring. This is what makes the horizontal case easier. When you haven't pulled on the mass at all, it will sit at the equilibrium length of the spring. And let's just recall from last semester what we mean by that. This is the length that the spring is when no force is exerted on it. And by Newton's third law, that means that when it's at this length, the spring exerts no force. Now, at any other length, the spring always pulls or pushes, as the case may be, back towards the equilibrium. So if we push the block a little bit this way, compressing the spring, then the force that the spring exerts on the mass is back opposite the direction we pushed the mass towards the equilibrium position. And no matter where we push the block, that force always points back towards the equilibrium position. And if we pull or push it farther from the equilibrium position, that force gets bigger. This is something we know about springs. So notice that this is a case where the force always points back towards the equilibrium position, and that means this is always a restoring force. And so this meets the condition that we expect for oscillations to happen, the presence of a restoring force. The restoring force that we get when we have a spring as the thing that supplies the force is special. Remember that for a spring force, the force is proportional to the displacement from equilibrium. So here's our relation. I've put vector symbols on to indicate that we're talking about direction. And remember that this delta x here is the displacement of the end of the spring from its equilibrium position. K is the stiffness of the spring, and this negative is just saying that whichever way the displacement from equilibrium is, the force exerted by the spring is opposite that, just like I've drawn here. Now, for our purposes, thinking about harmonic oscillators, it's always going to be convenient to set our origin, our axes, at the equilibrium position. And that leads to a nice little simplification, because with the axes there, now the displacement from equilibrium is just the same thing as the position. So instead of delta x, we can just write x. And furthermore, most of the time we're going to be restricting our attention to one-dimensional cases, and so much of the time we don't even care about these vector symbols because we're in one dimension, and just saying, say, right is positive and left is negative, or up and down, whichever the case may be, is all we need to do to keep track of all the direction information that we ever need. So a lot of the time we can just drop the vector symbols even. But the thing that's even more special is the form of the force due to a spring. It's a linear function of the position. Now, generally, when you have an oscillation, this isn't always the case, but for a mass on a spring it is, and it's going to turn out to lead to special behavior. So we tend to look out for this and say that this idea of a linear restoring force is the identifying feature of simple harmonic oscillations. Because if a mass on a spring acts this way because of this restoring force, any other system you come across that happens to also have a linear restoring force, you know that it's going to oscillate exactly the same as a mass on a spring. And so this is why this idea of simple harmonic oscillation is useful as sort of a category of motion, because it's not just masses on springs that do it. For example, pretty much all elastic forces are linear, and so things like vibrating strings and bending structures like buildings swaying in the wind end up having linear restoring forces, and so they execute oscillations that are just like a mass on a spring. But there are some other surprising examples. A pendulum, as long as it does small oscillations, as we'll see, turns out to have a linear restoring force, and so it also oscillates the same way as a mass on a spring does. And that's sort of surprising, the idea that a pendulum ends up carrying out the same sorts of oscillations as a mass on a spring is sort of surprising if you think about it, because they're very different systems. It turns out that there's a close relationship between simple harmonic oscillations and uniform circular motion, and this relationship is going to be useful to us. So you can show this relationship through an experiment. Here's how it works. You have a mass on a spring. So this is our simple harmonic oscillator. And you have an object on, say, a turntable or some other way of making something go in a circle. And you arrange it so that the period of this thing going around the circle is the same as the period of your simple harmonic oscillator. So that's one of the difficulties of the experiment. That takes some arranging. You also need to match the amplitude of the oscillation to the radius of the circle, and what's more, you need to get the equilibrium position of your oscillation lined up with the middle of the circle. And then you shine a light, and you're going to look at the shadows. And you set it up so that at the moment you release your mass, the shadows are on top of each other. And what you find then, as you watch it, is that the shadows stay exactly in sync with each other. They go around the circle in lockstep. Now, if you think about that, that's sort of surprising. These are very different motions. This thing is going in a circle. This is a mass on a spring. These are seemingly unconnected, and yet they move in lockstep. So this is a very useful little observation, and we're going to use it in a moment to develop some expressions that are going to be very useful for us analyzing simple harmonic oscillations. Here's a demonstration of this using a post on a rotating wheel and a pendulum, and you can see that the shadow of the post on the rotating wheel is doing a fairly good job of following the motion of the pendulum. Here's another demonstration of it using a ball on a rotating arm and another ball on a spring, and again you can see that they follow each other fairly well. When I describe this, students are often puzzled by why we need the radius of this circular motion to match the amplitude of the oscillatory motion, or why the periods have to match. If I draw you a couple of pictures, if you haven't seen why, you'll see why pretty quickly. So remember that the goal here is for the shadows of these two things to line up. So let's imagine the light is coming up, and so at the start they're lined up, and so their shadows are both sitting here on the screen. Now, let's suppose that we haven't lined up the equilibrium position of this mass on the spring with the center of the circle. And so let's say the equilibrium position is here. And that means that the amplitude of this oscillatory motion is like this, which does not match the radius. Now, that means that half a period later, the mass on the spring is going to be over here. But half a period later, the thing on the circle is going to be over here. And so its shadow is here, and the shadow of the oscillating object is here, and they haven't stayed lined up. So if the amplitude here doesn't match this radius, then there's no hope that these shadows will stay on top of each other. Let's suppose we have matched the amplitude of the oscillation to the radius of the circle. But let's say we've failed to match their periods. Now, think about a full period later when, say, this object on the circle has come back to its original position. But if the periods aren't matched, then the oscillatory object will not have completed a full period, and so it won't be back where it started. Maybe it might be, I don't know, over here or something. And so once again, the shadows won't have stayed lined up. And so there's no hope for the shadows to stay lined up if we haven't matched the amplitude with the radius and matched the periods. But the surprising thing is that if we do manage to match those, they do stay lined up. They're very different seeming motions. If you try this with some other motion, like matching a circular motion with an object bouncing back and forth between two walls at constant speed, if you match the periods and the distance between the walls and the radius and so on, then they'll be in the same place at the ends of the motion, but they won't stay lined up through the whole motion. So this is something that's very special about the relationship between circular motion and simple oscillatory motion, and we're going to be able to use it to show some things about simple harmonic motion. Let's look at what this close relationship between uniform circular motion and simple harmonic oscillations can tell us. Let's say we've done this setup. So we've got our circular motion with some radius and its uniform speed, and we've got our harmonic oscillation going on down here, and we've lined them up so that the equilibrium position of the mass is right here where I've put the axes, and that is lined up underneath the center of the circle. And let's say we've arranged for the amplitude of this to be the same as this radius, and for the periods to be synchronized. So let's just note that down. We have a period of the oscillator is the same as the period of the thing going in the circle, and we'll just call those both capital T. And we have the radius of the circle is the same as the amplitude of the oscillation. And now notice that this distance here, that is the x position of the thing going in the circle. But it's also the same distance as the x position of the oscillator. So the other thing we have is that x for the oscillator is the same as, this is really the x component of the position vector of the thing going in a circle. And these things are going to be the key for us being able to write down what the position of the oscillator is as a function of time. That's our goal here. I want to make sure you're following the argument. So I'm going to get you to do the next little bit of the reasoning. What we want to do is connect XO, the x component of the position of the oscillator, with r and theta, which we can use to describe the position of the object on the circle. So here's just a picture like what we were just looking at, and these two objects are staying lined up as they move, and the object on the circle has gone around some angle theta. And I want you to figure out what the correct relationship is between XO and r and theta. So if you are in the course, Moodle will now get you to answer this question. Otherwise, I suggest you pick an answer before you go on to the next part of the video.